This video is about derivatives of inverse trigonometric functions. For our notes, before we just list all the formulas, and there are many, it's nice to see how the formulas come about. So I want to explore one particular case of this, and it'll help give you an idea of where these formulas come from. And that is, let's explore where we want to find the derivative, d over dx, of sine inverse of x. Now, to do this, let's recall a couple things. If I let y equal sine inverse of x, which is what our function is at hand here we're trying to derive, then, given what we understand from trigonometry, if I were to apply the sine of both sides, this would be equivalent to saying that the sine of y equals x. In other words, what value, when plugged into the sine function, will give me x? That's what the output of the inverse sine function would mean. Now, we also know or recall that there are some restrictions with this. So with a sine inverse function, the y value, which is the output for the sine inverse, has to be between and including negative pi over 2 to positive pi over 2. Now you may say, well, I forgot all that trigonometry stuff. Okay, but this is going to come back to be involved in this example. So I'm just kind of bringing it back here for the moment. Now, if this is the case where I start with y equals sine inverse of x and find that to be the same as sine of y equals x, then we can use implicit differentiation to take the derivative of this implicit form, where if I take d over dx of the left side, which is just sine of y, and then set that equal to d over dx of the right side, which is just the x, then now what we know with implicit differentiation, on the left side, I could see this as a composite function. The outer function is the sine. The derivative of sine is cosine, but I keep the inner function as is at first, that's the y, but then I multiply by the derivative of that inner function, which would be then dy dx. Okay, so we've seen that already when we were discussing implicit differentiation. On the right side, I have d over dx of x. Well, x is already explicitly a function of x. That's just 1. Now, as you'll recall in implicit differentiation, you want to get dy over dx alone. And so if I continue to isolate that, I'll have dy over dx equals, and if I divide both sides by 1 over cosine of y, by cosine of y, I'll have 1 over cosine of y on the right side, and that's what dy dx is. Now, let's keep in mind the broader context. We're trying to find the derivative of sine inverse of x, but we've called that y, and so if I've now found dy dx, that's exactly what we've been trying to find from the beginning here. Now, the tricky part, though, is that I have it in terms of y, and I really don't want that. I'd like to find dy dx in terms of x. So what we can do is bring in the Pythagorean identity. So let's recall that sine squared of anything, we'll call it x, plus cosine squared of x equals 1. This would mean if I solve for cosine of x, in fact, to make it clear, let's go ahead and just use the letter y. The identity works for any variable. You could use theta, y, whatever. Let's just use y to make it clear. So if I have this Pythagorean identity, then I solve it for cosine of y. That will be equal to plus or minus the square root of 1 minus sine squared of y. Just solving this Pythagorean identity for cosine. But then the plus or minus gets settled because of this original restriction we noted way up here with our original inverse trig function. So the fact that y has to be between negative pi over 2 and positive pi over 2 means we have to use, in this case, the positive cosine value, because that's only quadrants 1 and 4. Okay, so let's put this back together. This really means 1 over cosine of y is really the square root of 1 minus the sine squared of y. But if you think back to what sine of y is, we already said that's really just x which means we could call this the square root of 1 minus x squared. And so this formula here we get at the end, 1 over the square root of 1 minus x squared, is what we could say is represented as dy dx, which is the derivative of this original sine inverse function. So, in summary, this process could be done with all the other trig functions. We have to memorize these. I'm just going to list them here in our notes. They look a little intimidating at first until you realize that it's all the stuff we know. I've let u equal some function of x so that you can see the chain rule happening in all of these formulas here, where you have to multiply by the derivative of the input at the end, that u prime at the end. And we get many cases here of these inverse trig derivative rules. Let's try an example where we want to differentiate the following function, y equals the tangent inverse of x minus the square root of 1 plus x squared. Alright, now this is clearly a tangent inverse function, and so we'd want to go up and use the formula for the tangent inverse derivative. But we also want to recognize that what's the input here, the x minus square root of 1 plus x squared, that's like our u in the formula. So we can say here y prime equals, now the derivative for tangent inverse is 1 over 1 plus u squared times u prime, if you go back up to the formula. But instead of writing u, we want to write what u is, which is this input. So we'll say 1 over 1 plus, and then instead of saying u squared, I'm going to write x minus the square root of 1 plus x squared in parentheses as the u being squared, times u prime is the derivative of that original input, which would be 1 minus, now if you think of this second root here with the chain rule involved, this would be a 1 half times 1 plus x squared to the negative 1 half. But then chain rule again, don't forget to multiply by the derivative of this inner function here, the 1 plus x squared. That would require us to multiply by 2x, its derivative. Alright, let's rewrite and expand this a little bit more. In this first part, we have this squared ugly term in the denominator. Let's expand that. So this is really 1 over 1 plus, and if I FOIL out the terms in these parentheses being squared, I'll end up with x squared minus 2x times the square root of 1 plus x squared, and then a plus 1, and then a plus x squared. You can double check the foiling on that. And then at the end, we have all this other stuff that the chain rule kind of popped out for us here. So we then multiply by a 1 minus 1 half times the 1 plus x squared to the negative 1 half, but then we're multiplying also by 2x there at the end, and the 2 from the 1 half and the 2 from the 2x would cancel. So altogether we end up with this 1 over. Now there are a couple different ways you really could force some simplification here that not every author or instructor may go through, but I'm going to show you one possible way to do this, and then there may be some variations in how to write this answer. If you take a look at this denominator that we have underneath the 1 here in this first term, really you could write this as, if you factor out a 2, it's really 1 plus x squared minus x times the square root of 1 plus x squared. Now that's not obvious, I understand, that's a little bit of algebra involved there. It might be easier to kind of go the opposite way and try to expand it. It's just combining terms and maybe factoring out the 2 from this previous denominator. Really we have that times this second part could be written as the square root of 1 plus x squared minus x all over the square root of 1 plus x squared. Now where did that come from? Well, really there are two terms there. This 1 plus x squared to the negative 1 half would be a denominator. If you got a common denominator, then this altogether here is what it'd end up as. And then if you took this square root of 1 plus x squared from the last denominator and distributed that into the parentheses that are in front of it, and then factored out the 1 plus x squared to the 1 half, or just 1 plus x squared at that point, you could simplify it even further to a final answer of 1 over 2 times 1 plus x squared. So that's like the simplest looking answer. There's a little bit of skipping steps involved in this from what I've written, but it algebraically works, and you may at least get to the point where if you've gotten to any part of this, that's a good sign. Keep checking it. Try the algebra. Practice simplifying it all the way to this point just to see if you can get it. Now let's try another example, and in this one we start with the function y equals cosine inverse of sine inverse of t. Well, if we go back up and understand what our inverse trig derivatives are, which eventually soon should be memorized, we can understand this is a composite function. We start with the chain rule with the outer function, the cosine inverse in this case, which is why we'll write negative 1 over the square root of 1 minus u squared. Well, u this time is the sine inverse of t. That's the inner function for the cosine inverse. So that's following the formula, of course. Then to use the chain rule, we'll have to multiply by the derivative of the u, du or u prime, and that would be the sine inverse t function. So the derivative of that would be 1 over the square root of 1 minus x squared, or in this case actually it's a t, so we'll use t squared. So this could be a way to simplify it. Again, could you possibly force that further? Yeah, I guess so, maybe, but this is plenty to show that you understand the rule and the way that composite functions should be derived.